right now as you watch this. Light from the most distant galaxy humanity has ever found is hurtling toward us at 186,000 miles per second, and that light began its journey when the universe was only a few 100 million years old, before Earth existed, before our sun ignited, long before the Milky Way became anything recognizable. But here's the part that shatters everything you think you know. Our observable universe doesn't contain hundreds of billions of galaxies. It contains trillions, and many of them shouldn't even exist according to our current physics. In the next moments, we'll dive through the cosmic web itself, witnessing colossal galaxy collisions, impossible structures, and ancient light that has crossed 13 billion years of darkness just to reach us. If you're ready to see the universe the way it truly is, let's begin Part 1. The true scale of the universe and galaxy count. The 2 trillion galaxy discovery. For decades, astronomers stood confidently behind their calculations. 200 billion galaxies. That number already seemed incomprehensible, didn't it? 200 billion separate island universes, each packed with hundreds of billions of stars. But when the James Webb Space Telescope aimed its revolutionary infrared instruments at patches of space that appeared completely empty, it didn't just update that number, it obliterated it. The real count: 2 trillion galaxies. Let that sink in for a moment. For every single galaxy scientists thought existed, 9 more were hiding in plain sight, too distant, too faint, too redshifted for our previous technology to detect. This isn't a small correction. This is discovering that 90% of all galaxies in the observable universe were invisible to us until now. Think about this confirmed fact in the time it takes you to read this sentence. Light from thousands of these newly discovered galaxies crosses another 100,000 miles of space toward Earth. Some of that light has been traveling since before our solar system condensed from a cloud of dust and gas. We're literally looking at baby pictures of the cosmos, and there are far more babies than we ever imagined. The Hubble Space Telescope gave us our first real hint that something was off with our galactic census. When astronomers pointed Hubble at what they called the ultra-deep field, they were taking one of the biggest gambles in the history of astronomy. They committed precious telescope time to stare at a region of sky that looked absolutely empty. Not just dark, empty. This patch was smaller than a grain of sand held at arm's length. For 11 straight days, Hubble collected light. 800 separate exposures. Over 260 hours of continuous observation aimed at apparent nothingness. When the data finally came back and researchers assembled the image, what they saw changed everything. 10,000 galaxies, 10,000 entire cosmic cities, each containing billions of stars, all crammed into a space that would be covered by the period at the end of this sentence if you held it against the night sky. But here's where your brain should start hurting. That ultra-deep field represents just 1/13 millionth of the entire sky. 1/13 millionth. Do the math with me here. 10,000 galaxies in 1/13 millionth of the sky. Multiply that by 13 million, and you start to grasp what we're dealing with. Except even that calculation was conservative, because Hubble could only detect the bright, nearby galaxies. Webb's infrared vision revealed everything else. Galaxies so distant that their light has been stretched from visible wavelengths into infrared. Radiation by the expansion of space itself. Galaxies so small and faint, they're like trying to spot a birthday candle on the surface of the moon. Each one represents hundreds of millions or even trillions of stars. Each one potentially harbors countless planets. Each one might contain civilizations looking up at their own night sky. wondering if they're alone. The mathematics becomes almost absurd at this scale. If every galaxy contained just 100 billion stars, which is actually on the low end for galaxies like our Milky Way, we're looking at 200,000 billion stars in the observable universe alone. That's a 2 followed by 23 zeros. More stars than grains of sand on every beach, every desert, every sandbox on planet Earth combined. And remember, this is just what we can observe. The actual universe extends infinitely beyond our cosmic horizon. What we see represents a tiny bubble in an ocean that might have no edge at all. But before we dive into that philosophical rabbit hole, let's focus on something even more mind-bending about these numbers: cosmic scale and the mathematics of infinity. Every single one of those 2 trillion galaxies tells a story that spans billions of years. Some are spiral galaxies like our own Milky Way, with elegant arms rotating through space over hundreds of millions of years. Others are massive elliptical galaxies, shaped like cosmic footballs, containing trillions of stars in chaotic orbits. Still others are irregular galaxies, shapeless collections of stars that defy easy classification. But what really matters isn't just the raw count. Let's put this in perspective using something you can actually visualize. Imagine you could count one galaxy every single second without stopping. No sleep, no breaks, just counting one galaxy per second. At that pace, it would take you more than 63,000 years to count all 2 trillion galaxies. That's longer than human civilization has existed. Now here's an even wilder way to think about it. The average galaxy contains around 100 billion stars, but galaxies range wildly in size. Some dwarf galaxies contain just a few million stars. Meanwhile, the largest known galaxies contain over 100 trillion stars. Let's be conservative and stick with that 100 billion average. 2 trillion galaxies times 100 billion stars per galaxy equals 200,000 billion stars. In scientific notation, that's 2 times 10 to the 23rd power. But scientific notation doesn't capture the sheer absurdity of this number, so let's break it down another way. If you could somehow visit one star every single second of your life, it would take you 6 quadrillion years to visit every star in the observable universe. The universe itself is only 13.8 billion years old. You'd need to live nearly 500,000 times longer than the current age of the universe to complete that journey. And we're still just talking about stars. We haven't even mentioned planets yet. Current estimates suggest there are more planets than stars in the universe. Possibly 5 to 10 planets for every star. That pushes the total planet count into numbers that have no meaningful comparison. We're talking about quintillions of worlds, the vast majority of which we'll never see, never study, never even know exist. But here's what keeps astronomers up at night. This entire cosmic inventory only accounts for about 5% of the universe's total mass and energy. Regular matter, the stuff that makes up stars, planets, and us, represents a tiny fraction of what's actually out there. The rest is dark matter and dark energy, mysterious components that we can detect only through their gravitational effects, but can't directly observe. Dark matter makes up about 27% of the universe. It provides the invisible scaffolding that allows galaxies to form and maintain their structure. Without it, galaxies would fly apart. The remaining 68% is dark energy, an even stranger phenomenon that's causing the expansion of the universe to accelerate. We can measure its effects precisely, but we have no idea what it actually is. So when we talk about 2 trillion galaxies, we're really only discussing the visible tip of a cosmic iceberg. The The universe is far stranger and more complex than these already incomprehensible numbers suggest. And that brings us to perhaps the most profound realization of all: the observable universe, boundary and beyond. Everything we've discussed so far, every single one of those 2 trillion galaxies, exists within what astronomers call the observable universe. This is a crucial distinction. The observable universe isn't the entire universe. It's just the portion from which light has had time to reach us since the Big Bang. The observable universe extends roughly 46.5 billion light-years in all directions from Earth. Wait, you might be thinking, how can we see 46.5 billion light-years away if the universe is only 13.8 billion years old? Shouldn't we only be able to see 13.8 billion light-years in any direction? This confusion stems from a common misconception about how cosmic expansion works. Light from the most distant galaxies didn't travel 46.5 billion light-years through static space. Instead, those galaxies emitted their light when they were much closer to us. But the expansion of space itself carried them farther away while their light was traveling toward us. Think of it like a cosmic conveyor belt. A galaxy emits light when it's, say, 10 billion light-years away. But during the 10 billion years it takes that light to reach us, space itself has expanded, carrying that galaxy to a current distance of 46.5 billion light. The light we're receiving now shows us what that galaxy looked like 10 billion years ago. But the galaxy itself is now much farther away. This creates something both beautiful and tragic. It means we're seeing the universe's history laid out before us in 3-dimensional time. The farther we look, the further back in time we see. The most distant galaxies appear as they were when the universe was less than 5% of its current age. We're watching cosmic dawn, the epoch when the first stars ignited and began illuminating a universe that had been dark for hundreds of millions of years. But it also means there's a fundamental limit to what we can ever observe. Light from regions beyond our cosmic horizon will never reach us, no matter how long we wait or how powerful our telescopes become. The expansion of space is carrying those regions away from us, faster than light can cross the intervening distance. This boundary isn't a physical wall. It's not like there's a barrier at the edge of the observable universe with a sign saying nothing beyond this point. The universe almost certainly continues beyond what we can see, possibly infinitely. But we're fundamentally limited to observing only the bubble of space from which light has had time to reach us. And here's where things get truly weird. If the universe is infinite, and current evidence suggests it might be, then everything that can happen will happen somewhere, not just once, infinitely many times. There would be infinite copies of Earth, infinite versions of you reading these words, infinite variations where you made different choices. This isn't science fiction speculation. It's the mathematical consequence of infinite space, combined with finite possible arrangements of matter. But even if the universe isn't infinite, it's almost certainly vastly larger than our observable bubble. Some estimates suggest the total universe could be at least 250 times larger than what we can observe. Others argue it could be infinite. Either way, those 2 trillion galaxies we can detect represent an infinitesimally small sample of everything that exists. Think about that for a moment. 2 trillion galaxies, each containing hundreds of billions of stars, trillions of planets, and all of it, every single galaxy we've ever observed or ever could observe, might represent less than 1% of what actually exists, possibly far less than 1%. Possibly an infinitesimal approaching zero. This is the scale we're dealing with. This is the universe we inhabit. A cosmos so vast that human language struggles to describe it, where numbers lose meaning, where our intuitions about space and time completely break down. And we're just getting started, because now that we understand how many galaxies exist, we need to talk about where we actually live in this cosmic ocean. We need to discuss our cosmic address, from our solar system to our galaxy to structures so large they make our entire galactic neighborhood look like a speck of dust. Are you ready to zoom out even further? Because what comes next will completely reshape how you think about home. Part 2. Galaxy groups, local structures, and our cosmic address. Right now, you're moving through space at over 1 million miles per hour, and you don't feel a thing. You're not just spinning with Earth's rotation or orbiting the Sun. You're being carried by the Milky Way galaxy itself as it barrels through the cosmos toward an inevitable destination. But where exactly are we going? And more importantly, where are we right now in this vast cosmic ocean we just explored? The local group structure. Our galaxy doesn't travel alone. The Milky Way belongs to what astronomers call the local group, a gravitationally bound collection of more than 50 galaxies all performing an intricate cosmic dance. This is our immediate neighborhood, our cosmic suburb, if you will. And like any neighborhood, it has its hierarchies, its bullies, and its quiet residents just trying to exist without causing trouble. The local group spans roughly 10 million light-years across. To put that in perspective, if our Milky Way were the size of a dinner plate sitting on a table in New York City, the local group would stretch all the way to Los Angeles. That's the scale of just our local neighborhood. Remember those 2 trillion galaxies we talked about? Well, 54 of them are our closest neighbors. 3 galaxies dominate everything else in the local group through their massive gravitational pull. These are the heavyweight champions of our cosmic corner. First up is the Andromeda Galaxy, the undisputed king of our neighborhood. Andromeda contains over 1 trillion stars and stretches 220,000 light-years across. That makes it roughly twice the size of our own galaxy. And here's the kicker. It's heading straight toward us at 68 miles per second. Let me repeat that. 68 miles per second. That's 244,000 miles per hour. In the time it took you to read this sentence, Andromeda closed the distance between us by about 300 miles. The collision is absolutely confirmed. Not a possibility, not a maybe. It's happening in approximately 4.5 billion years. We'll get to that cosmic catastrophe later. But just know that every second that passes brings Andromeda about 12 Earth lengths closer to us. Our Milky Way ranks second in the local group hierarchy. We're no slouch ourselves. Current estimates suggest we contain around 300 billion stars spread across 100,000 light-years. We're positioned about 26,000 light-years from our galactic center, safely tucked away in what's called the Orion Arm. That's one of several spiral structures that gives our galaxy its distinctive pinwheel appearance when viewed from above. Think about that location for a moment. We're about a quarter of the way out from the center, not in the bustling downtown core where stars are packed densely together, not in the remote outer suburbs where stars are sparse and lonely. We're in a comfortable middle zone. This location might not be an accident. The galactic center is a chaotic place, full of radiation and gravitational violence. The outer edges are cold and resource-poor. Our spot, just right for complex chemistry and stable planetary systems. The third major player in our neighborhood is the Triangulum Galaxy. This spiral beauty is about half our size, containing roughly 40 billion stars. While smaller than its two massive neighbors, Triangulum has something special going for it. It's producing new stars at nearly twice the rate of the Milky Way. It's like the young, energetic upstart of the local group, burning bright and fast, while the big guys have settled into middle age. But these three giants don't rule alone. They're surrounded by dozens of smaller satellite galaxies that orbit them like cosmic pets. Many of these satellites orbit our own Milky Way, held captive by our gravitational influence. The largest are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere as fuzzy patches of light that ancient cultures incorporated into their myth. The Large Magellanic Cloud contains about 30 billion stars, while its smaller companion hosts roughly 3 billion. These aren't insignificant numbers. 3 billion stars is still an incomprehensible amount of stellar real estate. But compared to the Milky Way's 300 billion, the Magellanic Clouds are like small towns compared to a major metropolis. And here's what's fascinating. These small galaxies are doomed. They're on a collision course with the Milky Way, expected to be fully consumed within the next 2 billion years. Beyond our local group satellites, we've got even smaller dwarf galaxies, dozens of them. Some contain just a few million stars, others might have a few hundred million. Many of these dwarf galaxies are so faint that we're still discovering new ones. Every few years, astronomers find another dim collection of stars orbiting in the outer reaches of our galactic neighborhood. It's like finding out your city has suburbs you never knew existed. What's striking about this local structure is how it mirrors patterns we see throughout the universe. Everywhere we look, we find this hierarchical arrangement. Small galaxies orbit larger ones. Large galaxies cluster together in groups. Groups cluster into larger structures. It's cosmic organization all the way up. And speaking of larger structures, the local group itself is just a tiny speck within something far more vast. The Laniakea supercluster and the Great Attractor. Here's your real cosmic address: Earth, Solar System, Orion Arm, Milky Way Galaxy. Local group, Virgo Cluster, Laniakea Supercluster. That last one, most people have never heard of it. And it wasn't even discovered until 2014. Think about that. Humanity only learned our true cosmic address a decade ago. Laniakea means immeasurable heaven in Hawaiian, and it's a fitting name for a structure so vast that light takes over 520 million years to cross from one end to the other. This supercluster contains roughly 100,000 galaxies. 100,000, each one potentially containing billions of stars, all connected by gravity into a single coherent structure. The discovery of Laniakea came from mapping the peculiar motions of galaxies throughout our region of space. See, galaxies aren't just being carried apart by cosmic expansion. They're also being pulled by gravity toward massive concentrations of matter. By measuring these motions, astronomers could trace the gravitational flows that define supercluster boundaries. What they found was astounding. The Milky Way, Andromeda, and tens of thousands of other galaxies are all flowing like water toward a massive gravitational anomaly at the center of Laniakea. This monster, called the Great Attractor, is located roughly 250 million light-years away. It has the mass of tens of thousands of galaxies and is pulling our entire cosmic neighborhood toward it at over 1,000 miles per hour. Let that sink in. Right now, as you're sitting there, you're being dragged through space at 1,000 miles per hour toward something so massive that it's affecting the motion of structures spanning hundreds of millions of light years, and you can't feel a thing. That's because everything around you, Earth, the Sun, the Milky Way, the entire local group, is all moving together in the same direction. But here's where it gets even weirder. The Great Attractor itself is moving. It's being pulled toward an even larger structure called the Shapley Attractor, located roughly 700 million light-years away. And that structure is probably being pulled by something even larger. It's cosmic flows within flows, like rivers feeding into larger rivers that empty into oceans. The Virgo cluster sits near the center of Laniakea and serves as the dominant gravitational influence in our cosmic region. This cluster contains over 2,000 galaxies, including several giant elliptical galaxies that rank among the most massive in the known universe. The cluster's total mass is roughly 1 quadrillion times that of our Sun. 1 quadrillion solar masses, all concentrated in a region about 50 million light-years across. Our local group occupies a relatively quiet region on the outskirts of Laniakea. We're in the cosmic suburbs, far from the violent cluster environments where galaxy collisions and harassment are common. This peaceful location might have been crucial for allowing complex life to evolve on Earth. In the dense cluster cores, radiation levels are higher, galaxy collisions are frequent, and stable planetary systems are harder to maintain. The structure of Laniakea reveals the cosmic web in action. Massive filaments of dark matter and galaxies connect the major galaxy clusters, while vast voids separate different regions of the supercluster. Our local group sits on one of these filaments, connected to the larger cosmic architecture but isolated, enough to avoid the destructive processes that occur in denser environments. But even Laniakea isn't the end of the story. This immense supercluster represents just one node in an even larger network, stretching across billions of light-years. The Perseus Pisces supercluster, the Hydra Centaurus supercluster, dozens of other massive structures, all create a cosmic web pattern that extends to the limits of our observable universe. Understanding our cosmic address system. Let's put this all together so you can understand exactly where you are right now in the grand scheme of things. Think of it like a mailing address, but instead of street, city, state, country, we're going planetary system, galaxy, galaxy group, supercluster. Starting small, you're on Earth, the third planet, orbiting a yellow dwarf star we call the Sun. That star is one of about 300 billion stars in the Milky Way galaxy. Our galaxy is the second largest member of the local group, which contains 54 galaxies spanning 10 million light-years. The local group is part of the Virgo cluster, which contains over 2,000 galaxies. And the Virgo cluster is just one component of the Laniakea supercluster, containing 100,000 galaxies across 520 million light-years. But here's what really matters. Every single component of this address is moving. Earth orbits the Sun at 67,000 miles per hour. The Sun orbits the Milky Way center at about 500,000 miles per hour, taking roughly 230 million years to complete one full rotation. The Milky Way is moving toward Andromeda at 244,000 miles per hour, and our entire local group is being pulled toward the Great Attractor at 1,000 miles per hour, while simultaneously being carried by cosmic expansion. Add all those motions together, and you're moving through space at roughly 1.3 million miles per hour relative to the cosmic microwave background. That's the closest thing we have to an absolute reference frame in the universe. Every second of your life, you travel about 360 miles through space without feeling any of it. By the time you finish reading this section, you'll have traveled thousands of miles through the cosmos. Now here's the philosophical gut punch. For all these vast scales we've been discussing, for all these superclusters and galaxy groups, Our entire cosmic neighborhood represents just one small region of the observable universe. Laniakea, with its 100,000 galaxies, represents just 0.005% of all galaxies in the observable universe. Our home supercluster, this structure so vast it defies human comprehension, is just a tiny decoration on one thread of the cosmic web. And remember, the observable universe itself might be just a tiny fraction of the total universe. So when you think about your cosmic address, you're not just living in a city or a country or even on a planet. You're living in a specific galactic suburb, in a specific galaxy group, in a specific supercluster, in a specific section of the observable universe, in a possibly infinite cosmos that extends forever in all directions. Does that make you feel small? It should, but here's the thing. Every single atom in your body was forged in the hearts of massive stars billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was created through nuclear fusion in stellar cores and scattered through space when those stars exploded as supernova. You're not just living in the universe, you're made of it. You're a way for the cosmos to know itself. But our peaceful suburban existence in the cosmic web masks a violent reality that's been unfolding for billions of years. Because while we've been comfortable out here in the galactic outskirts, the Milky Way has been busy. It's been eating its neighbors, it's been growing through conquest, and it's about to get much, much worse. What happens when galaxies collide? What does it look like when cosmic titans weighing trillions of times more than our sun meet in catastrophic violence? And what will happen when Andromeda finally arrives at our doorstep in 4.5 billion years? The answers are more spectacular and terrifying than you can imagine. Part 3: Galactic Violence, Collisions, and Cosmic Cannibalism. The Milky Way is a monster, and it's been eating its neighbors alive for over 10 billion years. Right now, as you read these words, our galaxy is in the process of violently tearing apart and consuming at least 2 smaller galaxies. This isn't ancient history. This is happening in real time, on a cosmic scale that spans millions of years but never stops. The Milky Way's galactic cannibalism. The Sagittarius dwarf elliptical galaxy is dying. Slowly, painfully. It's being shredded by our galaxy's gravitational field like paper in a cosmic blender, leaving behind streams of stars that wrap around the Milky Way like spaghetti on a fork. These stellar streams stretch for hundreds of thousands of light years, marking the death trail of a galaxy that once contained billions of stars. Think of it like a massive whirlpool in the ocean encountering a small fishing boat. The dwarf galaxy gets stretched and twisted by tidal forces that are literally ripping individual stars away from their home and flinging them into the Milky Way's outer halo. Some of these stellar refugees will eventually settle into stable orbits around our galactic center. Others get ejected entirely into the dark void between galaxies, doomed to wander alone forever. Meanwhile, the Canis Major dwarf galaxy has already met an even worse fate. This galaxy was so thoroughly destroyed that astronomers only discovered its remains in 2003. Its corpse is scattered across our galaxy's outer regions, with individual stars now permanently mixed into the Milky Way's population. It's like a murder mystery, where the body was hidden in plain sight for billions of years. The evidence for this ongoing galactic cannibalism is written in the stars themselves. Astronomers can identify which stars originally belonged to destroyed galaxies by studying their chemical composition and orbital patterns. It's cosmic forensics. Stars from the Sagittarius dwarf, for example, have a distinctly different mix of heavy elements compared to stars born in the Milky Way. They're immigrants from a destroyed homeland, carrying the chemical signature of their lost galaxy. But here's what's truly fascinating. The Sagittarius dwarf isn't going down without a fight. Its disruption is triggering waves of star formation throughout our galaxy's spiral arms. As the dwarf galaxy's gas clouds collide with material in the Milky Way's disk, they compress and heat up, creating stellar nurseries where new stars are born at an accelerated rate. In a twisted way, the death of one galaxy feeds the birth of countless new stars in another. The Large and Small Magellanic Clouds are next on the menu. These two galaxies, visible to the naked eye from Earth's southern hemisphere, are currently about 160,000 light-years away from us, but they're not in stable orbits. Astronomers have confirmed that both Magellanic Clouds are on a collision course with the Milky Way, expected to be fully consumed within the next 2 billion years. When the Large Magellanic Cloud finally merges with our galaxy, the event will be spectacular. We're talking about 30 billion stars being absorbed into the Milky Way. The collision will trigger massive bursts of star formation that will light up the night sky with brilliant nebulae. It will potentially wake up the supermassive black hole at our galaxy's center, turning it into a quasar that outshines entire galaxy clusters. If humanity still exists 2 billion years from now, they'll witness one of the most dramatic cosmic events possible from a front row seat. This galactic cannibalism isn't unique to the Milky Way. The Andromeda Galaxy has been even more aggressive in consuming its neighbors. Astronomers have identified the remains of at least 10 different dwarf galaxies in Andromeda's outer regions. The evidence suggests it devoured most of them within the last few billion years. Some of these ancient meals are still visible as faint streams of stars stretched across hundreds of thousands of light-years, like breadcrumbs marking where galaxies used to be. The process follows a predictable pattern throughout the universe. Larger galaxies grow by consuming smaller ones, which in turn had previously consumed even smaller systems. It's a cosmic food chain that's been operating since the first galaxies formed over 13 billion years ago. Big fish eat little fish, and the biggest fish of all. They're about to collide. The Andromeda Milky Way collision. In 4.5 billion years, the night sky will be on fire. The Andromeda Galaxy is racing toward us at 68 miles per second. That might not sound fast compared to the speed of light, but at cosmic scales, it's like two freight trains barreling toward each other on the same track. The collision is inevitable, confirmed, and it will completely reshape both galaxies in the most violent cosmic event our region of space has ever experienced. The Hubble Space Telescope settled the question definitively in 2012 by measuring Andromeda's sideways motion across the sky. For decades, astronomers knew the galaxy was approaching us, but they couldn't determine if it would be a direct hit or a near miss. Hubble's precise measurements revealed the terrifying truth. Andromeda is aimed directly at the Milky Way's heart. When galaxies collide, it's not like two solid objects smashing together. Remember, galaxies are mostly empty space. The average distance between stars is about 25 trillion miles, so the chance of any two stars actually hitting each other during the merger is essentially zero. Your odds of winning the lottery 1,000 times in a row are better than two stars colliding during a galactic merger. Instead, what happens is far more dramatic and chaotic. The collision will unfold over hundreds of millions of years, beginning with the outer edges of both galaxies starting to warp and stretch. Massive tidal forces will fling entire star systems out of their home galaxies and into the dark void between them. Some of these ejected stars will carry their planets with them, creating orphaned solar systems drifting forever through intergalactic space. Imagine being on a planet in one of those ejected systems. One day you look up and see your home galaxy receding into the distance. Within a few million years, both the Milky Way and Andromeda would be faint smudges on opposite sides of the sky. Your entire civilization would exist in complete isolation, billions of light years from the nearest galaxy. No other stars visible in your night sky, just darkness and two distant fuzzy patches that were once your galactic homes. As the two galactic centers draw closer, their supermassive black holes will begin a deadly spiral dance. The Milky Way's central black hole contains about 4 million times the mass of our Sun. Andromeda's is significantly larger, at roughly 100 million solar masses. When these monsters finally merge, they'll create gravitational waves so powerful they'll ripple through the fabric of space-time itself. Detectable by civilizations billions of light years away, the merger will trigger the most spectacular fireworks show in cosmic history. Gas clouds from both galaxies will collide and compress, igniting massive bursts of star formation that will light up the combined system like a cosmic Christmas tree. New stars will be born at a rate 10 times faster than what we see in either galaxy today. The combined galaxy will blaze with the light of trillions of newborn stars for hundreds of millions of years. Earth's fate during this collision depends on cosmic luck. Computer simulations suggest there's roughly a 50% chance our solar system will be flung 3 times farther from the galactic center than we are now. There's also a 12% chance we'll be ejected from the merged galaxy entirely, sent wandering through the darkness between galaxy clusters. And there's a very small chance, maybe 2%, that we could be flung inward toward the galactic center. But here's the truly mind-bending part. If humanity still exists when this collision begins, we'll have front row seats to watch it unfold over millions of generations. The night sky will gradually fill with new stars as Andromeda grows larger and brighter. Eventually, it will dominate the entire sky, a spiral of fire stretching from horizon to horizon. The view from Earth during peak merger will be unlike anything we can see today. The final product of this cosmic catastrophe will be a giant elliptical galaxy that astronomers have already nicknamed Milky Way. It will be roughly 10 times more massive than either original galaxy, and will rank among the largest galaxies in our local supercluster. But the beautiful spiral arms that define both the Milky Way and Andromeda today, gone, scrambled into a chaotic elliptical blob by the violence of the collision. Dead galaxies and the quenching mystery. But not all galaxies die through violent collisions. Some galaxies simply turn off, and scientists have no idea why. Max 21291 looks like a perfectly normal spiral galaxy from a distance. It spins. It has elegant curved arms. It contains several times more mass than the Milky Way. But when astronomers looked closer, they discovered something that breaks every model of galaxy evolution we have. This galaxy stopped forming new stars over 10 billion years ago. 10 billion years. When the universe was less than a quarter of its current age. It became a cosmic zombie that still exists, still rotates, but contains no spark of new life within it. And this shouldn't be possible. Dead galaxies, or quenched galaxies as astronomers call them, are systems where star formation has completely shut down. In a normal galaxy like ours, massive clouds of gas and dust constantly collapse under their own gravity to birth new generations of stars. This process should continue for trillions of years until the universe itself expands so much that galaxies can no longer hold onto their gas supplies. But Max 2129 to 1 defied this natural order. Here's the problem. According to our best models, this should be impossible for a galaxy of its size and type. Small galaxies can be quenched relatively easily. A nearby supernova explosion or the gravitational influence of a larger galaxy can strip away their gas supplies, effectively sterilizing them. But massive spiral galaxies like MAX 21291 should have enough gravitational pull to hold onto their gas no matter what cosmic violence occurs around them. The mystery deepens when you examine the galaxy's internal structure. Most dead galaxies that astronomers have found are elliptic C-shaped, resembling cosmic footballs with stars distributed roughly evenly throughout. These shapes make sense because they typically form when two spiral galaxies collide and merge, scrambling their organized structure into a random blob. But MAX 2129-1 maintained its spiral structure even as it died. It's like finding a perfectly preserved body that looks completely alive from the outside but contains no heartbeat, no breath, no sign of life within. The galaxy's stars are still arranged in elegant, curved arms radiating out from a central bulge, exactly like a living spiral galaxy. But spectroscopic analysis reveals no young blue stars, no star-forming regions, no stellar nurseries, just old, red stars slowly dying with no replacements being born. Several theories attempt to explain this mystery, but none are fully satisfactory. One possibility is that the galaxy's central supermassive black hole went through an extremely active phase, generating powerful jets and radiation that heated up all the surrounding gas to the point where it could no longer collapse into stars. This process, called active galactic nucleus feedback, can suppress star formation, but it usually doesn't completely sterilize a galaxy of this size. Another theory suggests that the galaxy experienced a series of massive supernova explosions that collectively blew away its entire gas supply. But the math doesn't work out. You'd need an unrealistic number of supernova all exploding within a relatively short time period to eject enough gas to completely shut down star formation in a galaxy this massive. The most disturbing possibility: we're missing something fundamental about how galaxies evolve. MAX 2129-1 might represent a completely unknown process that can kill even the largest, most robust galaxies without warning. Some cosmic mechanism we haven't discovered yet. Some phase of galactic evolution that our theories don't account for. And this dead galaxy isn't alone. Astronomers have now identified dozens of similar systems scattered throughout the distant universe. All massive spiral galaxies that somehow died billions of years before they should have. Each discovery adds another piece to a cosmic puzzle that seems to grow more mysterious rather than clearer. Jellyfish galaxies and ram pressure stripping. If dead galaxies represent slow, mysterious death, jellyfish galaxies show us violent, spectacular destruction in real. ISO 13701, located 220 million light-years away, is caught in the act of being destroyed. The galaxy appears to be swimming through space, trailing long tentacles of gas and stars behind it, like a cosmic jellyfish. But this isn't a peaceful swim. This galaxy is drowning. The destruction is caused by ram pressure stripping, one of the most violent ways a galaxy can die. Imagine driving a convertible at highway speeds through a torrential downpour. The wind doesn't just get you wet, it strips the rain right off your windshield and flings it backward. Now scale that up to cosmic proportions. ESO 137-01 is racing through the Perseus galaxy cluster at over 1,000 miles per second. The space between galaxies in this cluster isn't empty, It's filled with extremely hot gas, heated to temperatures of over 100 million degrees Fahrenheit. This gas is so thin that it would count as a perfect vacuum by Earth standards. But when you're moving through it at cosmic speeds, it becomes like hitting a brick wall. The ram pressure from this hot intergalactic medium is literally stripping away ESO 137's own gas supplies. The galaxy's outer layers are being peeled off like the skin of an onion, creating spectacular trails that stretch for over 200,000 light-years behind the galaxy. These trails contain enough material to form billions of new stars. But instead of fueling the galaxy's growth, this precious star-forming gas is being scattered into the void, lost forever. What makes the imagery even more striking is that the stripped gas doesn't just disappear. As it gets torn away from the galaxy, it forms intricate structures that really do resemble the tentacles of a jellyfish. These tentacles are illuminated by ultraviolet radiation from young, hot stars that are still forming within the stripped material, creating an eerie blue glow against the darkness of space. The process is irreversible and ultimately fatal. Once a galaxy loses its gas supplies, it can no longer form new stars. The existing stars will continue shining for billions of years, but gradually the galaxy will fade as its most massive stars burn out and explode as supernova. Eventually, only dim red dwarf stars will remain, turning the once vibrant galaxy into a cosmic ghost. Astronomers have identified dozens of these jellyfish galaxies throughout nearby galaxy clusters. Each one tells the same tragic story. They're all caught in different stages of the stripping process. From galaxies just beginning to lose their outer gas layers to systems so thoroughly destroyed that only faint tentacles remain of what was once a thriving stellar metropolis. The most haunting aspect of jellyfish galaxies is what they represent: cosmic beauty born from cosmic violence. These systems are among the most photogenic objects in the universe. With their streaming tentacles and bright blue, star-forming regions creating images that belong in an art gallery. Yet each jellyfish galaxy represents the death throes of a system that might have harbored billions of worlds and potentially entire civilizations. Galaxies without dark matter. But even the violent destruction of jellyfish galaxies seems normal compared to galaxies that challenge our most basic understanding of reality itself. NGC 1277 shouldn't exist. Its very presence is breaking our understanding of how the universe works. This galaxy contains virtually no dark matter, which is like finding a skeleton without bones. Dark matter makes up roughly 85% of all matter in the universe. It provides the invisible scaffolding that allows galaxies to form and maintain their structure. Without it, galaxies should either fly apart or never form in the first place. Yet NGC 1277 is sitting there in space, apparently held together by nothing but the gravity of its visible stars, and nobody knows how that's possible. This discovery sent shockwaves through the astronomical community when it was announced in 2018. For decades, the existence of dark matter has been considered one of the fundamental pillars of modern cosmology. We can't see it, we can't touch it, we don't know what it's made of, but we know it's there because its gravitational effects are visible everywhere we look in the universe. Dark matter acts like invisible glue that holds galaxy clusters together. It's what allows spiral galaxies to spin without flying apart. It's what creates the cosmic web of filaments that connects all the large-scale structures in the universe. Without dark matter, the cosmos would look completely different. Galaxies as we know them couldn't exist. NGC 1277 is what astronomers call a relic galaxy, meaning it formed early in cosmic history and has remained largely unchanged for billions of years. It's several times more massive than the Milky Way and packed into a much smaller volume, making it incredibly dense compared to modern galaxies. But despite containing hundreds of billions of stars, measurements show it has virtually no dark matter halo surrounding it. The initial discovery was controversial because it seemed to violate everything astronomers thought they knew. Several teams of scientists double-checked the measurements, looked for errors in the data, and proposed alternative explanations. Maybe the galaxy was closer than originally thought, which would change the mass calculations. Maybe it had been somehow stripped of its dark matter by interactions with neighboring galaxies, but follow-up observations confirmed the impossible. NGC 1277 really does appear to be a massive galaxy with little to no dark matter. The finding was so significant that it required scientists to seriously reconsider some of their most basic assumptions about how the universe works. One proposed explanation is that NGC 1277 formed through an extremely rare process, where normal matter was somehow separated from dark matter during the galaxy's birth. Another possibility is that the galaxy's dark matter was stripped away by gravitational interactions with the massive Perseus galaxy cluster where NGC 1277 resides. But the most disturbing possibility: our entire understanding of dark matter is fundamentally flawed. Maybe what we interpret as dark matter is actually a modification to the laws of gravity that behaves differently under certain conditions. If that's true, then NGC 1277 might be showing us what galaxies look like when this modified gravity effect is somehow turned off. The discovery has opened up new questions that astronomers are rushing to answer. Are there other galaxies like NGC 1277 hiding in the universe? Could entire regions of space exist where dark matter is absent? And what does this mean for our understanding of how structure formed in the early universe? What's certain is that NGC 1277 represents a cosmic anomaly that challenges everything we thought we knew about reality. And it's not the only weird galaxy out there. Because in the early universe, when the cosmos was young and wild, even stranger things were happening. Things that make dark matter-free galaxies look almost normal by comparison. Part 4. The Early Universe, Extreme Galaxies, and Cosmic Dawn. There's a galaxy in the early universe where the gas clouds are shining brighter than all the stars combined. Scientists are calling it a totally new phenomenon, and it's rewriting what we thought we knew about the first billion years after the Big Bang. Welcome to the epoch of cosmic weirdness, where everything we observe seems to violate the rules we thought governed galaxy formation. Galaxies with superheated gas outshining stars. GSND G9422 exists from a time when the universe was only 1 billion years old, less than 10% of its current age. When astronomers first looked at its spectrum of light, they found something that had never been seen before. The signature of superheated gas that was actually outshining the galaxy's entire stellar population. This shouldn't be possible. Yet there it was, staring back at them from the data. In normal galaxies, stars are by far the brightest objects. They're nuclear fusion reactors converting matter into energy at temperatures of millions of degrees, pumping out enormous amounts of light across all wavelengths. The gas between stars, while important for forming new stars, typically glows much more faintly and only shows up in specific narrow wavelengths. But GSND G9422 flips this relationship completely upside down. The galaxy's gas clouds are being heated to over 140,000 degrees Fahrenheit, nearly twice as hot as the surface of typical massive stars. At these extreme temperatures, the gas becomes so energetic that it outshines the very stars that are supposed to be heating it. It's like finding a pot of water boiling furiously over a candle flame. The physics just don't add up, according to our standard models. The discovery came from the James Webb Space Telescope's infrared spectrograph, which can break down the light from distant galaxies into its component wavelengths, like a cosmic prism. When lead researcher Alex Cameron first examined the data, his reaction was immediate. "That's weird," and in astronomy, weird is exactly what you want to find. Weird means you're discovering something new, something that doesn't fit the textbooks. The spectrum showed clear signatures of highly ionized gas, meaning the atoms in these clouds have been stripped of most of their electrons by intense radiation. This level of ionization requires an enormous input of energy, far more than what the galaxy's observed stars should be able to provide. Working with computer models, the research team concluded that GSND G9422 must contain stars that are much hotter and more massive than anything we see in the local universe today. These primordial monsters might reach temperatures of over 140,000 degrees at their surfaces, making them incredibly efficient at pumping out ultraviolet radiation. Stars this extreme don't exist in the modern universe because they burn out incredibly quickly, living just a few million years before exploding. But in the early universe, conditions were different. The first generations of stars were built from pure hydrogen and helium with almost no heavy elements. This different chemistry allowed them to grow much larger and burn much hotter than modern stars. The implications extend far beyond just one weird galaxy. This gas outshining phenomenon might represent a missing link in our understanding of how the universe evolved, from its dark ages into the star-filled cosmos we see today. During the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen gas that blocked most light from traveling very far. Something had to ionize all that hydrogen to make the universe transparent. Astronomers have long suspected it was the first generation of stars, but regular stars don't seem capable of producing enough ultraviolet radiation to do the job. Galaxies like GSND G9422, with their superheated gas and ultramassive stars, might be showing us exactly how cosmic reionization happened. These extreme stellar populations could have pumped out enough high-energy radiation to ionize the entire universe over a few 100 million years. The red monsters and impossible early galaxies. The James Webb Space Telescope has found galaxies that are so massive and formed so early that they're breaking our models of how the universe should work. 3 galaxies, nicknamed the Red Monsters, contain as much mass as our entire Milky Way, but they existed when the universe was less than 1 billion years old. That's like finding a fully grown adult at a preschool. According to our best theories of galaxy formation, these massive systems shouldn't have had enough time to assemble so early in cosmic history. Galaxy formation was supposed to be a gradual process. Small clumps of dark matter slowly growing larger through gravitational attraction, eventually becoming massive enough to trap gas and begin forming stars. This process should take billions of years to create galaxies as large as the Milky Way. But the red monsters appear to have compressed this entire evolutionary sequence into less than 1 billion years. They're forming new stars at nearly twice the rate of similar mass galaxies today, suggesting that star formation in the early universe was far more efficient than our models predict. And they're not alone. Webb is finding massive early galaxies everywhere it looks, creating what researchers are calling a too many, too massive problem. The red monsters get their name from their distinctive appearance in Webb's infrared images. They glow with a deep red color because they're packed with dust, which absorbs blue and ultraviolet light from their stars and re-emits it as infrared radiation. This dust content is itself another mystery, because dust grains form from heavy elements that are produced inside stars over multiple generations. How did these early galaxies accumulate so much dust so quickly? Each red monster contains roughly 300 billion stars, comparable to the total stellar mass of the Milky Way, but they're packed into much smaller volumes, making them incredibly dense compared to modern galaxies. Their central regions probably contain stellar densities thousands of times higher than what we see in our galactic neighborhood. Imagine if, instead of the few stars visible in our night sky, you could see thousands of stars brighter than Venus, filling the entire sky from horizon to horizon. What makes the finding even more puzzling is that these massive galaxies seem to be converting a much higher percentage of their available gas into stars than should be possible in normal galaxy formation. Supernova explosions and radiation pressure from massive stars blow away most of the gas that could potentially form stars. This feedback mechanism prevents galaxies from becoming too massive too quickly. But somehow the red monsters overcame this natural limitation. They managed to hold on to their gas supplies and convert them into stars with unprecedented efficiency. It's like finding a factory that operates at 200% capacity without any of the usual problems that should shut it down. The physics just doesn't work according to our current understanding. Either we're missing something fundamental about how gas behaves in the early universe, or our models of feedback processes are completely wrong. The discovery of the red monsters represents a crisis in cosmology. Not the kind of crisis that means everything is wrong, but the kind that means we're missing crucial pieces of the puzzle. And that's exciting, because it means there are new physical processes operating in the early universe that we haven't discovered yet. New mechanisms that can build massive galaxies faster than we thought possible. The most distant galaxy ever discovered. We are looking at the most distant object ever discovered by humanity. Jade's GSE-140 exists from when the universe was only 280 million years old. The light reaching us today from this cosmic infant began its journey over 13.5 billion years ago, when the first stars were just beginning to illuminate a universe that had been dark for hundreds of millions of years. This galaxy earned its status as the distance record holder by shattering the previous record by 20 million years. That might not sound like much, but in the context of the early universe, 20 million years represents a significant fraction of the total time that had elapsed since the Big Bang. Finding galaxies that existed even earlier than expected keeps pushing back our understanding of when galaxy formation began. The galaxy's discovery required pushing the James Webb Space Telescope to its absolute limits. Even with Webb's unprecedented infrared sensitivity, Jade's GSC-140 appears as just a few pixels of reddish light against the cosmic background, but those pixels contain information that has traveled farther through space and time than any signal humanity has ever detected. The extreme distance means we're seeing this galaxy at a redshift of 14.44. Redshift measures how much the expansion of the universe has stretched the wavelengths of light during its journey to us. A redshift of 14.44 means the galaxy's light has been stretched by a factor of over 15, moving even its ultraviolet emissions into the infrared wavelengths where only Webb can detect them. What makes Jade's GSC-140 even more remarkable is that it's not just distant, it's also surprisingly massive and bright for such an early galaxy. The system contains several 100 million times the mass of our Sun, all packed into a region spanning roughly 1600 light-years across. that's incredibly compact compared to modern galaxies, suggesting that star formation in the early universe was much more concentrated and intense. The galaxy appears to be in the midst of a furious burst of star formation, creating new suns at a rate that would build the equivalent of our entire solar system every few years. This level of activity produces so much ultraviolet radiation that it ionizes the surrounding gas, creating a bubble of transparency in what was otherwise an opaque universe. This galaxy was literally helping to clear away the cosmic fog that filled space during the Dark Ages. Spectroscopic analysis confirmed its extreme distance and revealed that the galaxy contains surprisingly heavy elements for such an early system. The presence of oxygen and other metals indicates that multiple generations of massive stars had already lived and died by the time we're seeing this galaxy. That suggests star formation began even earlier than 280 million years after the Big Bang. Maybe as early as 150 or 200 million years. The galaxy's existence raises profound questions about how structure formed in the early universe. Current models predict that it should have taken longer for dark matter halos to grow massive enough to host such bright galaxies. JADES GSC 140 suggests either that galaxy formation was more efficient than we realize, or that the early universe contained physical processes we haven't yet discovered. Cosmic dawn and the first billion years. Perhaps most mind-boggling is the realization that we're seeing JADES GSC 140 as it appeared when the universe was still emerging from its cosmic dark ages. This was an era when most of space was filled with neutral hydrogen gas that blocked light from traveling very far. The galaxy we're observing existed at the very beginning of cosmic reionization, when the first stars began clearing away this primordial fog. The epoch between 200 million and 1 billion years after the Big Bang represents the most dramatic transformation in cosmic history. This era, called Cosmic Dawn, witnessed the birth of the first stars, the formation of the first galaxies, and the complete restructuring of all matter in the universe from a dark, neutral fog into the transparent, star-filled cosmos we see today. Before Cosmic Dawn, the universe was literally dark. No stars existed to produce light. The cosmic microwave background radiation had cooled below visible wavelengths, leaving space filled with nothing but invisible, neutral hydrogen gas and mysterious dark matter. If you could somehow travel back to this time, you wouldn't be able to see your hand in front of your face, no matter how powerful your flashlight. But hidden within this darkness, gravity was slowly assembling the first structures. The tiny variations in the density of dark matter, imprinted during cosmic inflation just after the Big Bang, grew larger over millions of years. These dark matter halos eventually became massive enough to trap the surrounding hydrogen gas, creating the raw material for the first stars. The very first generation of stars, known as Population 3 stars, were unlike anything that exists today, with no heavy elements available except what was created during Big Bang nucleosynthesis. These primordial giants, formed from pure hydrogen and helium, computer models suggest they were monsters containing hundreds of times more mass than our Sun and burning at temperatures hot enough to synthesize the first carbon, oxygen, and iron in the universe. These stellar behemoths lived fast and died young, exploding as hypernovae after just a few million years. Their deaths seeded the surrounding space with heavy elements, allowing the second generation of stars to form with more diverse chemistry. It was this second generation that began assembling into the first true galaxies. Galaxies like JADES GSC 140 and the red monsters represent this second generation caught in the act of rapid assembly. The James Webb Space Telescope is giving us our first direct glimpses of cosmic dawn by detecting galaxies from this crucial epoch. Each discovery is like finding a fossil from the early universe, preserving conditions that existed over 13 billion years ago. And what's emerging from Webb's observations is a picture of cosmic dawn that's far more violent and chaotic than astronomers expected. The early galaxies are more massive, more active, and more numerous than our models predicted. Star formation rates in these systems are off the charts, suggesting that the first billion years of cosmic history were characterized by incredibly rapid and efficient galaxy assembly. It's like the universe hit the ground running, building massive structures far faster than we thought possible based on the slow, gradual assembly predicted by our theories. The process of cosmic reionization. The light from these primordial galaxies also carries information about the process of cosmic reionization. As the first stars began pumping out ultraviolet radiation, they gradually ionized all the neutral hydrogen in the universe, making space transparent for the first time since the cosmic microwave background was released 380,000 years after the Big Bang. This reionization process wasn't uniform. It began around the most massive early galaxies and slowly spread outward, creating bubbles of ionized gas that eventually merged to encompass the entire universe. Webb can actually map this process by studying how the light from distant galaxies is absorbed by intervening neutral hydrogen. The more neutral hydrogen, the more absorption. By measuring this absorption at different distances, astronomers can trace how reionization progressed over hundreds of millions of years. Each new galaxy discovered from cosmic dawn adds another piece to this puzzle. We're learning that the transition from darkness to light happened faster and more dramatically than anyone imagined. The universe went from being completely dark to hosting massive bright galaxies in less than 1 billion years. A cosmic transformation that ranks among the most important events in the history of everything. But these individual early galaxies represent just single data points in a much larger story. To really understand cosmic dawn, we need to see how these galaxies fit into the larger cosmic architecture. We need to zoom out from individual galaxies to see the structures they're building, the filaments, the clusters, the cosmic web that will eventually connect everything in the universe. And that's exactly where we're heading next. Because the story of galaxies isn't complete until we understand the invisible scaffolding they're built on. The dark matter web that gave birth to everything we see. The largest structures in the universe that make entire superclusters look like tiny decorations. We're about to go from the smallest galaxies to the biggest structures in existence. Are you ready? Part 5. Cosmic Architecture. The universe's largest structures and infinity. The universe is built like a cosmic spiderweb. Massive filaments of dark matter and galaxies stretching across distances so vast they make entire superclusters look like tiny decorations. These galaxy filaments are the largest known structures in the universe, commonly reaching 160 to 260 million light-years in length. But some filaments are true cosmic monsters, the cosmic web and galaxy filaments. The largest confirmed structure is called the Hercules Corona Borealis Great Wall, stretching over 10 billion light-years across space. That's roughly 1/10 the diameter of our entire observable universe. If you could somehow travel at the speed of light, it would take you 10 billion years just to cross from one end of this structure to the other. Let that sink in for a moment. A single structure spanning 10 billion light-years. These filaments form the backbone of cosmic architecture, connecting galaxy clusters and superclusters in a vast three-dimensional web that spans the entire universe. The pattern resembles a neural network or the internal structure of a living cell, with dense nodes connected by elongated strands and vast empty spaces between them. Is the universe itself alive in some way we don't understand? The similarity is striking enough to make you wonder. The cosmic web emerged from tiny quantum fluctuations that existed just after the Big Bang. During cosmic inflation, these microscopic variations in density were stretched to astronomical scales. Over billions of years, gravity amplified these small differences, causing matter to flow along paths of least resistance between the densest regions. Dark matter led this cosmic construction project because it interacts only through gravity. Dark matter could begin clustering as soon as the universe became cool enough for stable structures to form. Normal matter followed the dark matter's gravitational lead, flowing along the same pathways to create the galaxy filaments we observe today. The space between galaxies within these filaments isn't empty. It's filled with warm, hot intergalactic medium, a tenuous gas heated to temperatures between 100,000 and 10 million degrees Fahrenheit. This gas is so thin that it barely qualifies as matter by Earth standards. But there's so much of it spread across such vast volumes that it contains more normal matter than all the stars in all the galaxies combined. Think about that contradiction. More matter exists in the nearly empty space between galaxies than in all the stars we can see. The universe is mostly empty space, filled with invisible hot gas, with tiny islands of dense matter we call galaxies scattered throughout, like cities in a vast desert. Cosmic voids, the great nothing. Between the massive filaments and great walls lie regions of space, so empty that they make the vacuum between stars look crowded by comparison. Cosmic voids are the largest empty spaces in the universe, spanning hundreds of millions of light years, with almost no galaxies, stars, or even dark matter within them. The Boat's void, also called the Great Nothing, exemplifies the extreme emptiness of these cosmic deserts. This spherical region spans roughly 330 million light-years in diameter, but contains almost no galaxies in its interior. If the Milky Way had formed in the center of the Boat's void, the nearest galaxy would be over 150 million light-years away, making it invisible to all but our most powerful telescopes. To understand just how empty these voids are, consider that the average density of matter throughout the universe is roughly 6 hydrogen atoms per cubic meter. That's already incredibly sparse by everyday standards. But within cosmic voids, the density drops to less than 1/10 of this universal average, creating regions that are emptier than the best vacuums we can create in laboratories on Earth. These voids didn't form through some cosmic explosion that cleared out the matter. Instead, they represent regions where the initial density of matter after the Big Bang was slightly lower than average, while gravity was pulling matter together to form filaments and galaxy clusters. These underdense regions became even emptier as their sparse matter was gravitationally attracted to the denser regions surrounding them. Living in a cosmic void would provide a profoundly different perspective on the universe. Instead of seeing thousands of galaxies scattered across the night sky, you'd see perhaps a handful of faint smudges representing the most massive galaxy clusters on the void's boundary. The universe would appear far more empty and desolate than the rich tapestry of stars and galaxies visible from our location within the cosmic web. Which perspective is more accurate? Are we living in an unusually dense region, or are void dwellers living in unusually empty regions? The answer depends on your frame of reference, but it raises fascinating questions about how location shapes perception of reality itself. Galaxy cluster collisions and cosmic violence. right now. For massive galaxy clusters are colliding in the most violent event our universe has witnessed since the Big Bang itself. The collision is taking place in galaxy cluster MACS J0717, located 5.4 billion light-years away. Each of the 4 clusters contains hundreds of galaxies and trillions of stars, plus enormous quantities of hot gas and dark matter. When objects this massive collide, they release more energy than the explosion of billions of supernovae happening simultaneously. The clusters are approaching each other at speeds of thousands of miles per second, their mutual gravity accelerating unimaginable amounts of matter toward an inevitable collision that will reshape an entire region of space. The Chandra X-ray Observatory has captured stunning images of this collision in progress, revealing the hot gas within each cluster glowing at temperatures of over 100 million degrees Fahrenheit. As the clusters merge, their gas clouds collide and compress, heating the material to even more extreme temperatures and creating shock waves that propagate outward for millions of light years. But the most fascinating aspect of this collision is how it separates different types of matter through the violence of the impact. The hot gas in each cluster experiences friction and turbulence during the collision, causing it to slow down and lag behind. But the galaxies themselves, being much denser and more compact, pass through the collision zone with relatively little interaction. The dark matter in each cluster behaves similarly to the galaxies, feeling only gravitational forces and passing through the collision with minimal interaction. Gravitational lensing observations reveal the dark matter distribution during these cosmic crashes, showing how the invisible scaffolding of the universe responds to extreme gravitational stress. The Bullet Cluster represents one of the most studied examples of this type of collision. 2 galaxy clusters collided at such high speed that their hot gas was completely separated from their galaxies and dark matter. The resulting configuration provided some of the strongest evidence for dark matter's existence, since gravitational lensing showed that most of the mass in the system was located with the galaxies rather than the hot gas. These cosmic battles represent the final stage of structure formation in our universe. As dark energy accelerates the expansion of space, galaxy clusters will become increasingly isolated from each other. The era of major cluster collisions will eventually come to an end, leaving behind a universe of isolated galaxy clusters separated by ever-expanding cosmic voids, the missing baryons and intergalactic medium. For decades, half of all normal matter in the universe was missing, hidden in a cosmic fog so thin and hot that it was essentially invisible. The mystery began with precise measurements of the cosmic microwave background, which revealed exactly how much normal matter was created during the first few minutes of cosmic history. But when astronomers tried to find all this matter by counting stars, gas, clouds, planets, and everything else they could observe, they came up short. They could only account for about half of the normal matter that should exist. The rest had simply vanished from the cosmic census. The solution came from fast radio bursts, brief flashes of radio waves from distant galaxies that last just milliseconds but release more energy than our sun produces in an entire day. When these signals travel through space, they interact with free electrons in the intergalactic medium, creating a measurable delay that depends on how many electrons the signal encountered during its journey. By studying the dispersion of dozens of fast radio bursts from known distances, astronomers could calculate the total number of electrons along each line of sight. The results solved the missing baryon mystery definitively. The lost matter was hiding in plain sight as hot ionized gas spread throughout the filaments connecting galaxy clusters. This warm hot intergalactic medium is heated to temperatures between 100,000 and 10 million degrees Fahrenheit, making it extremely difficult to detect directly. The gas is so thin that a volume the size of Earth's atmosphere would contain less matter than a single breath of air. But there's so much space between galaxies that even this incredibly tenuous material adds up to enormous total mass. Beyond the observable universe, outside the boundaries of everything we can ever observe, lies infinite mystery that dwarfs our observable universe beyond all comprehension. Current evidence suggests our universe might be infinite in extent, containing infinite galaxies, infinite stars, and infinite copies of every possible configuration of matter. In an infinite universe, every possible arrangement of atoms must occur somewhere, including exact copies of Earth, the solar system, and even you reading these words right now. This isn't science fiction. It's the logical consequence of our best understanding of cosmic geometry and fundamental physics. The observable universe extends roughly 46.5 billion light-years in all directions from Earth, giving it a diameter of about 93 billion light-years. But the actual universe almost certainly extends far beyond our cosmic horizon. What we can see represents a tiny bubble in an ocean that might have no edge at all. After flying through 2 trillion galaxies across 13.8 billion years of cosmic history, we return to the most profound question: what does this mean for us? Every galaxy we've explored formed through the same fundamental processes that created our own Milky Way. The carbon in your body was forged in nuclear furnaces of massive stars. The oxygen you breathe came from stellar explosions. You are literally made of star stuff. We are temporary arrangements of atoms in an infinite cosmos, but we are also the universe's greatest achievement. Matter organized in such a way that it can understand its own existence and contemplate the infinite mystery surrounding us on all sides. A final thought before you go. Tonight, when you step outside and look up at the stars, remember this: you're not just looking at distant points of light, you're looking at 2 trillion galaxies, each one a universe unto itself. You're seeing light that has traveled for billions of years just to reach your eyes in this exact moment. You're witnessing the universe's story written across the canvas of space and time. And perhaps most beautifully, you're part of that story. Every atom in your body was born in the heart of a dying star. Every breath you take connects you to the cosmic web stretching across infinite space. You are the universe experiencing itself, a brief but brilliant spark of consciousness in an endless ocean of stars. We started this journey asking how many galaxies exist. We found 2 trillion in our observable universe alone, possibly infinite beyond what we can see. But more importantly, we discovered that in a cosmos this vast, this ancient, this incomprehensibly large, the fact that you're here, right now, aware and wondering about it all, is perhaps the most extraordinary thing of all. So tonight, before you sleep, take a moment, look up if you can, and know that while we may be small, we are also impossibly precious. Cosmic accidents that became conscious. Stardust that learned to dream. Thank you for joining me on this journey through every galaxy in our universe. May your dreams be as infinite as the cosmos itself, and may you always remember that you carry the stars within you. Rest well, fellow traveler. The universe will still be here tomorrow, waiting to share more of its secrets. Good night.